All right. Good evening, everyone. Celso Batalha Choten. And today at midnight, midterm number 3 is going to be open and is going to be available tomorrow. So we have 1 hour to take a shot at midterm number 3, which is going to be the last one. And I will allow a retake and taking the highest score of both exams for your midterm number 3 grade on Saturday. So Saturday I'm opening again. You're not going to see the same questions, maybe, but you have a second chance. And the subject is primarily what we studied so far, um, um, properties of stars, star formation, low massive star, and high massive star. So we have up to midnight tomorrow to get it done, and it's going to be open midnight tonight. So we are now, when we initiated the course, we have a overview of astronomy from ancient times, and we play a little bit with the history of astronomy, because when you look up to the sky, you see planets and stars with an apparent motion. So the main subject of the first few chapters is to explain why this motion occurs. So exactly what's going on. And then we learn that Earth has a rotation that gives rise to day and night. But in addition to rotation, Earth also goes around the sun, and this yearly revolution gives rise to the fact we see certain types of constellations or certain constellations in certain months of the year, and we don't see in others. Because as Earth goes around the sun, the night part of Earth gets exposed to different parts of the celestial sphere. And there is a third motion that is kind of a subtle. You can probably detect it if you have consecutive observations over more than 100 years, which is difficult, and that is called precession. So precession is probably the main cause that leads to astrology as it was thought 3,000 years ago. Right now, if astrologers still propose astrology as a viable way to explain people's behavior, they have to fudge information, they have to hide certain informations where the sun is at certain times of months of the year, because it doesn't match. The sky is different from what it was 4,000 years ago. In fact, this information kind of passed very, very fast through the hands of astrologers, and they don't explain this to people in general. So now you have studied that subject, and you know. But then once we finish with this observational astronomy and we learn about light, then we dive into a different part of astronomy, that is how to explain what is very far away, how to explain stars, how to explain what the stars are made of. And then we emphasize the tools astronomers have to explore the cosmos. And primarily these tools is based on the fact we know how light behaves. And the two main tools are spectroscopy and photometry. So photometry is a technique that measures the amount of radiation and light we received on a certain color band. And spectroscopy is a technique by which you take light and then you spread light over different color bands, and you analyze in detail what's going on in each of these color bands. And then you might be able to locate absorptions and emission lines, and you might, by modeling these lines, you might be able to infer the properties of the gas responsible for producing these types of transitions. And as we learn properties of stars, then we also explore how stars were formed. So they are not formed out of nothing. They have a whole process of star formation we studied in the very few chapters before today. And it is required cold gas, and requires that gravity is efficient enough to initiate a contraction in these giant molecular clouds that eventually leads to what we call protostar. And then the star goes its merry way as a main sequence up to the point that eventually stars cease to exist. They undergo changes, the core becomes more compact because can't lead to more fusion reactions, the outer layer expands, and the star becomes a red giant star. Now we are going into a different realm. So the first one was pretty much historical and how we observe the sky from down here. The second one is the tools astronomers have to explore the cosmos and what exactly stars are and how they are important to provide us with material, with stuff that forms our body, our environment. Now, the third part of this class, which initiates today, has to do with the universe in large scale. So, what is the universe exactly in large scale? And more so, how the universe came to start in a given time in the past. Did the universe have a beginning? That's the main question. It's a fundamental question. Like another one, why the night sky is dark? Why is it dark? Right? If you might think, well, this seems to be a silly question, but it's not. So if you consider stars as people in the past considered, if you consider the stars don't go through a life cycle and they are eternal, so once they are formed or created by some magician, they are there forever. So if the stars are there forever, and if the universe is infinite, which means you have infinite number of stars, which means the light of all these infinite stars have had enough time to arrive at us, here at us, where we are, which means the night sky should be pretty much bright, right? So, but it's not, it's dark. So why is that? So people just in philosophical arguments thousands of years ago, they claimed there was a beginning. The universe had a beginning because it's dark. If it were infinite and eternal, then we would have had enough time, because eternity is pretty big time, for the light of these very far away objects arrive here and give us some sort of a radiation. So, but anyway, so this subject is going to be explored at the end of these sections on the universe in large scale. So today we start with one of these main elements in the universe in large scale, and that is galaxies. So galaxies come in different flavors and shapes. So let me show you pictures. By the way, what a galaxy is. So galaxies are complex systems of hundreds of billions of stars. And since now we know that for each star in our galaxy, at least, there are a large number of planets associated with the stars, then the number of planets, the number of systems out there is magnificent. So here I'm showing you a few examples of galaxies, and they have specific names based on their morphology. For instance, here you have a collision of two galaxies, and these two galaxies are spiral. They have this spiral feature, which we are going to study with more detail later. And obviously there is an interaction, kind of a collision between these two galaxies, which leads to one of the important aspects of our universe in large scale, and that is galaxies were formed a long time ago, 10 billion years ago. And once they were formed, no more galaxies are being formed now. But those that exist are undergoing transformations. They are interacting, they are merging, they are clustering, and here's a nice example of one of these galaxy collisions, right? This could be also interpreted as galaxy collision. So they are obviously certainly interaction interacting. Here, another example of a collision of galaxies. So just think about it, hundreds of billions of stars in each one of them colliding and forming that system. This looks like our nearby Andromeda galaxy is a spiral galaxy, and all these little dots you see around, these, they are stars in our own galaxy that happen to be in the way of our visualization. It's another example of galaxy here. So galaxies are classified in three main branches. One branch is the so-called spiral galaxy, and this image here is a good representation of what that is. It's one that has a center, right? It's called bulge, has spiral arms that come out of the center part named bulge, and surrounding the galaxy altogether has a major region that's called halo. So spiral galaxies have the halo, have the spiral arms, have the bulge. And what is interesting about spiral galaxies, as we see in chapter 14, is that they still have star formation process going on because they do have cold gas that happen to exist in the spiral arms. So spiral galaxies have spiral arms, and the spiral arms is populated by cold gas that harbor giant molecular clouds. And we saw that giant molecular clouds are responsible for providing the ingredients, the main ingredients for star formation, cold gas. And here and there, gravity can efficiently start the contraction process that will lead to a protostar formation. Another type of galaxy is called elliptical galaxy. Let me see if I can find one here. Or let me call the name elliptical galaxies. Elliptical galaxies, as you will see here, don't have spiral arms. Still going? Yeah. So elliptical galaxies don't show spiral arms. It's just a smooth distribution of brightness from the center part all the way to the outer skirts of these galaxies. So elliptical galaxies, contrary to spiral galaxies, they are not forming new stars. They do not have cold gas, which means star-forming regions do not exist, and the star-forming process do not exist anymore. So elliptical galaxies, they can appear in different shapes. For instance, this elliptical galaxy is slightly more elongated than the other one we saw. In fact, this looks like more a spiral galaxy, but it's called elliptical. It has a spiral structure here, but it's named as elliptical galaxy. I don't think this is elliptical galaxy. Doesn't look like. Don't trust anything you see, everything you see in the internet. So here's another example of elliptical galaxy surrounded by satellites. See this? It's a bunch of galaxies in the same region they are. These little dots here could be stars in our Milky Way that happen to be in the way from us, in between us and this cluster of galaxies. But if you look carefully, this is a galaxy, this is a galaxy, the far back is a galaxy, this is a galaxy. This happens to be an elliptical galaxy, a giant elliptical galaxy located in the center part of a cluster of galaxies. You can see another one here, kind of lost in there. This fuzzy thing is another galaxy down here. So elliptical galaxies, they can appear as giant and as dwarf. Here's an example of a dwarf galaxy, dwarf elliptical galaxy. It has also this elliptical structure, kind of an oval structure, but if you look carefully, it's not is not a smooth distribution of light or brightness from the center to the outer edge. You can see the pixels. Every single dot representing one of the stars in that particular galaxy, which means that galaxy is not that big. It's a dwarf galaxy, dwarf elliptical galaxy. So elliptical galaxies, they appear themselves in a range, in a wide range of sizes. They can be dwarf, called dwarf galaxies, or they can be giant elliptical galaxies. As opposed to spiral galaxies, they are always the same size, more or less, 100,000 light years in dimension. Okay. So elliptical galaxies, let's take a look at the third type of galaxy there is, and they are called irregular galaxies. Irregular galaxies. As the image might show, irregular galaxies don't have any specific shape. In fact, they might be considered the leftovers of interactions like this one. So there is not a specific shape. And they are very much rich in gas. They do have star formation going on, but they don't have any specific shape. 50% of the material in this type of galaxies are pretty much gas, which means you expect to find star-forming regions on them. If you visit the southern hemisphere, there are two galaxies you can see with the naked eye. They are called Magellanic Clouds. Oops. And they are beautiful, so even if you have moon in the sky, you can see them quite well. These two fuzzinesses that are in fact a couple of irregular galaxies that right now are interacting with our own Milky Way. They are about 150,000 light years away, so they are relatively close, and they are colliding with Milky Way. So if we give enough time, these two clouds, they are not clouds, they are galaxies, will merge eventually with our Milky Way galaxy. So in the universe in large scale, how the universe in large scale is organized? Well, it's organized in galaxies that happen to be clusters in what we call clusters. There are clusters, there are poor clusters, and our Milky Way galaxy happen to be located in a so-called poor clusters of few dozens of galaxies. It's called the local cluster, cluster of galaxies, and Milky Way and Andromeda are two of the biggest galaxies in it. It's about 3 million light years in extent. And but these there are also rich clusters of galaxies, not with a few dozen galaxies, but with 1,000 members. Just stop and thinking. Thousands of galaxies in a single cluster, and each galaxy with their own hundreds of billions of stars. And each stars, now we know, have their own group of planet systems, its own planetology, own satellites, and so that is the universe we are, just to give an idea. And these clusters of galaxies, it doesn't stop there. The universe in large scale is organized in what we call super clusters of galaxies, consisting of several clusters, some of them poor, right, like ours, some of them rich, like Virgo with 1,000 members. They all connected by gravity field surrounding regions that have no material, called voids, and these voids is where the so-called dark energy we are going to study is responsible for expanding and providing what the Hubble flow, the expansion, the universal expansion we detect. So again, in large scale, so if you look in any direction, the so-called cosmological principle that we study in chapter 1 indicates no matter which direction you look, the universe looks about the same in large scale. It's a distribution of superclusters of galaxies with voids in every single direction seems about the same. So it's isotropic, which means no matter which direction you look, the universe seems to be the same, and also doesn't have a center. So we are not in the center of the universe. So no matter where you are, you should be able to observe the same characteristic. So the universe in large scale is homogeneous, consisting of superclusters of galaxies surrounding voids, and the superclusters of galaxies in their turn is a combination linked by gravitational forces of clusters of galaxies. And these clusters of galaxies, gravitationally speaking, is glued. This gravitation is gluing few or several thousands of galaxies, and each galaxies have, it's infinite, not infinite. Billions is a lot of a big number of stars, but billions of stars, and that's where we are. If you take an astro tour, what goes on in the core of galaxies? Let's see if this can pull up.
Some galaxies emit huge amounts of energy from a tiny region in their nucleus. In some cases, such as in the still visualization shown here, this tiny region can outshine all the billions of stars in the galaxy. What generates all the energy in these active galaxies?
So that is the point I was trying to make. When galaxies were formed billions of years ago, the region near the center is where the gas was most concentrated. So when stars were formed, the first generation was formed, the first generation exploded, you have the first black hole, and that black hole happened to be in an environment very much rich in gas that kept on falling on it, to the point that this black hole became larger and more active. What you're seeing here is a result of bipolar flow. This orange or reddish flow is a bipolar, which is the result of conservation of angular momentum. So gas is falling onto the hole, and the hole can't handle all this angular momentum, and gas is shoot out in a bipolar way.
Galactic nuclei, AGN. How can so much luminosity come from such a compact source? Let's zoom into the center of the AGN for a close look at the source of the energy. We will begin with a simplified view and gradually build up to a more accurate model. At the very center of an AGN is a black hole, a body with a mass more than 1 million times greater than our Sun, yet only a few times larger in diameter. The intense gravitational field of the black hole prevents any light from escaping it. Since no light leaves its surface, the black hole appears black. However, the black hole is not alone. Gas and dust circle it in an accretion disk orbiting the black hole at high speed. Gas close to the black hole orbits at a high speed due to the intense gravitation.
So the process we are seeing here is exactly, physically speaking, is exactly the same process that led to star formation. So here we are talking about the formation of a black hole in the center of a galaxy with hundreds of billions of stars. But the physics that leads to this accretion disk around a protostar is exactly the same physics that leads to the formation of an accretion disk in the core of a galaxy, which is a much larger system.
Pole of the black hole. Gas at a larger distance orbits more slowly due to the weaker gravitational force. As a result, atoms in neighboring rings of gas will pass each other in their orbits. The friction between gas particles in neighboring rings heats the gas. The hot gas emits electromagnetic radiation, causing the accretion disk to glow. Because the motions are most violent close to the black hole, friction heats this gas to very high temperatures. Farther from the black hole, gas moves more slowly, the friction is more gentle, and the temperatures are lower. Gas emits different kinds of electromagnetic radiation depending upon its temperature. The coolest gas emits long wavelength radio waves. Warm gas emits infrared radiation. Hot gas emits visible light. The very hot gas close to the black hole emits X-rays. Most of the gas very close to the black hole will eventually spiral into the hole and disappear. However, due to strong magnetic fields near the black hole, a small fraction of the ionized material shoots outward perpendicular to the disk, making a pair of narrow jets. The particles in these jets are expelled at nearly the speed of light. The jets shoot out into intergalactic space along the galaxy's axis of rotation. As the relativistic particles gradually lose their energy, they eventually turn into large blobs of hot gas. Astronomers call these blobs radiolobes because they emit strongly in the radio portion of the spectrum. Current models of AGN explain many of the observed phenomena, emission of radiation over a wide range of wavelengths, from radio to X-ray, red-shifted and blue-shifted emission lines.
So, the simulation shows the physics that surrounds these black holes in galaxies. But again, the physics is exactly the same, the one that surrounds the formation of protostars, as we saw in chapter 5 and 6 or so. Okay. So tomorrow, in fact, tomorrow I will not be probably I will not be able to get home on time. Probably I will. I'm not sure yet, because I have a meeting at Evergreen, and if I get in traffic, just wait for me. But I will open the chat room anyways, somewhere around 7 or 7:30. But tomorrow I might be a little bit late because I have to leave Evergreen late. So we are pretty much going to the large scale universe, galaxies today. Tomorrow we are going to explore in more detail the spiral arms, why the spiral arm exists, and what type of material exists in there and in the region between the spiral arms, and what formed them. And then we have to close with Milky Way galaxy and cosmology. Okay. So let me stop taping. So good night to all of you,